When I was an undergrad student and I started studying exciton physics and light matter interactions in general, I remember reading in many of the papers and books about this topic things like the oscillator strength in this system is small and therefore this transition has a lower probability to happen and so on. And I remember that I was confused, like, oscillator strength, where's the oscillator here? What is oscillating here? So then afterwards I realized that there is a kind of a very simplistic model for light absorption, and this is what I'm going to discuss now. So the idea is, what we are studying here is the polarization of a system of electrons, and this polarization is going to be defined as the dipole moments of the system divided by the volume. And the dipole moments of all the electrons in the system, I'm going to write it here like a number of electrons multiplied by the charge of the electrons, and x, which should be a position with respect to the equilibrium position of these electrons. So I'm already assuming that they are going to oscillate around this equilibrium position. So here's the volume. Now I'm going to redefine this thing as a density. So this is going to be an n0. And I'm going also to redefine this thing as the dipole moment, for example. I could put a d here. So sometimes they rewrite this polarization as being something like n0d. So this is what I'm going to study now. And what I'm going to show is that this polarization, when you put light in a system, then it's going to be time dependent, or actually we normally write it in a way that is like frequency dependent. So this frequency dependence is going to be seen in this x here. So what I'm saying is I have already electrons in this system that are oscillating for some reason. We are going to discuss these reasons later on in this video, but let's say that they are already oscillating for some reason. Then you have electron mass and the acceleration of these electrons. This is going to be proportional to some force that should be a kind of minus m omega 0 squared x. This would be a normal oscillator. So I'm going to include also some terms like a damping term, 2m gamma. This is going to be important later on, as you're going to see. So this is 2m gamma multiplied by the velocity. So this is a damping term. And I'm going to add a force that comes from the electric field of the light. So this is going to be something like the electron charge multiplied by the electric field of light here, E of t, right? So now I have this x that is a function of time, and I have this electric field from the light that is also a function of time, right? So I'm going to assume that this light that I'm using here is monochromatic. So this is going to be something like E of t is actually some constant multiplied by cosine of omega t, for example. Or you can also write something like E0 e to the minus I omega t. And actually let us write this thing more like in an omega, with an omega dependence, right? So I would have something like that. Then I'm going to try a solution like an ansatz, that is x of t is going to be x of omega e to the minus I omega t, which follows more or less the same pattern as the electric field. So let's try a solution like that. You impose the solution in the equation. So now what we are going to see is m, then you have minus omega squared, then plus, I'm going to put all these terms to the other side of the equation, right? So this is going to be plus omega 0 squared and minus 2 gamma, and the derivative here will give you a term like an omega here, right, with I. Then this is all multiplied by x of omega. This is going to be equal to minus to plus E and the field. But then I'm going to cancel these signs here. So I'm going to put this as plus. This is going to be minus. This is plus. And this is minus now. So now I can solve this thing for x as x of omega is equal to E over m multiplied by 1 over omega squared minus omega 0 squared plus 2 gamma omega I, and this is multiplied by the electric field, right? So I'm going to do something else here. I'm going to multiply everything by this n0 and this E here, because then I can identify my solution here as being the polarization itself. So I have n0E multiplied by that would be E squared n0 and this term here, and this is the polarization itself, right? So this is P of omega. Now I can even rewrite this thing like I can put all these terms together here and call these things the chi of omega, and this equation is going to be rewritten in this form now. So polarization as a function of omega, this is going to be a chi of omega multiplied by E of omega. So now you see that what I have here is something that is an analog of what you have in magnetism, that normally you have a quantity that you call magnetization, for example, and this magnetization is proportional to the magnetic field, and the proportionality is given by this term here, which multiplies the magnetic field, right? So now what I have is an electric analog of that. So I have a polarization by an electric field. It depends on the electric field that I put here, and the number that connects these two quantities is this one, and this is going to be an omega dependent susceptibility. So in the same way that we call this thing in magnetic fields as magnetic susceptibility, I'm going to call this thing also a kind of an electric susceptibility. But as this one depends on omega, it's not for a normal field, it's for a oscillating field with frequency omega. So I'm going to call this thing the optical susceptibility, because it will be related to light, right? So now what we have to do here is to study the characteristics of this optical susceptibility and how does this relate with light absorption and so on, right? So let us rewrite this optical susceptibility here. I'm going to put this in another page. Chi of omega, you can rewrite this thing as like minus n0 E squared over then I'm going to do this as I'm going to redefine this omega 0 in a different way. I'm going to do this like that. So it's easy to check that this expression gives you the same expression as I put in the previous page. If I define that omega 0 prime is going to be the square root of omega squared minus gamma squared. Omega 0 squared minus gamma squared. So this damping term here, if I say that this damping term is very small, then omega 0 prime is going to be more or less the same as the omega 0 itself. So the original frequency of this oscillator, right? So, okay, now I'm saying that I have electrons and they are making a polarization inside the material, for example, and that is it's very closely related to what we call the displacement field, that in this case now I'm going to say that the displacement field depends on omega, on some frequency, and this should be the electric field that you have in the system. This is actually a vector, right? So it's the electric field plus the field that has been induced by the dipoles that were polarized in the system, right? So I should put something like 4 pi multiplied by these dipoles, and this is 4 pi in CGS units, right? And if I rewrite this thing in the way I just defined it here, because I just found that I can write a P of omega as a susceptibility multiplied by the electric field, right? So this, I can rewrite this as 1 plus 4 pi chi of omega, multiplied by the field. So now what I have is something that I can define as an effective dielectric function, right? So this is something like the dielectric constant of the system, but now it's no longer a constant. Now it's going to be dependent on omega. So I'm saying that depending on the frequency of the light that you are using in the system, because of these dipoles that were generated, and these dipoles, they change with time. Now I'm saying that I don't have a dielectric constant anymore in the system. What I have is a dielectric function, and it's a function of the frequency here, right? So if I want to write this definition of dielectric function, I can write it as 1 plus 4 pi. Now actually there is actually a minus here because there is a minus sign here, right? So let's correct this thing here. I would write as minus 4 pi and 0 e squared over this. And now I'm going to write this term the same as I did before. So some people redefine this thing in another way. They put all these terms together and they call this thing the omega PL, or plasma frequency squared. So what is the plasma frequency here? Why do I call this plasma frequency? That's because let's discuss more or less what is happening here. I'm saying that there is a density of electrons that are oscillating with time, right? So let's call this density n. This is a function of position and time, for example. And this density of electrons is moving with time. So I should be able to write a continuity equation because this is a density. So densities in continuous system, they should obey a relation like the derivative of n as a function of time should be, if you add it to the divergence of the current, this should be 0, right? But actually current in this context is going to be given by, current is the density itself multiplied by E multiplied by V, right? And these are all things that change with position and time, right? So they should all be put into this equation here. There is something else happening here. There is another equation that you should take into account, which is the Maxwell equation for the electric field, the what we normally call source equation. That would be divergence of the electric field should be given by 4 pi E, and the density, that in this case should be what changes from the original density in the system, right? So n minus n0. N0, remember that n0 is the actual the density that I had in the beginning. So I'm now saying that the density is changing with time, and it changes obeying these three equations at the same time. So I'm going to, there is another one here. That is the Newton's equation for this system, which says that mass multiplied by the acceleration, which in this case I'm going to put in terms of velocity because velocity is already here. So dv dt, that should be the electric field that I have in the system, which is the only force that I have. So charge multiplied by the electric field, actually, right? So these are the equations that should be satisfied at the same time. So what I'm going to do is approximation, a kind of a linearization of all these equations, because if I plug in all the equations one into the other, you are going to find a very high order equation here. So what I'm going to do is I'm going to say that the density here is actually n0 plus some n1, and there will be some corrections of order delta squared here too, but I'm going to neglect these corrections. I'm going to say that they are not so important then. I would do the same for the velocity, but I'm saying that the velocity here is the electron starts with 0 velocity, so I only have a term like d multiplied by v1. And for the electric field it's the same. I'm saying that in principle these electrons are the system is not polarized, there should be no electric field and so on. So I should put just a term like d delta E1. Now you substitute these things into the equations, you are going to find something like actually this thing, there should be an E here, because you have the current here is already defined with the charge too, right? So this is a charged density, and also this one should have a charge in it. So it's this charge here. So now what I'm saying is if I input these things in this equation, I'm going to find E, then the derivative of n0 is going to be 0, so all you'll find is derivative of n1 in time, and now divergence of this j, that would be something like n0 e v1. Keep in mind that I'm taking only first order terms, so I would have something like n1 v1 too, but that would be a second order term in delta, and I'm saying that everything that is second order in delta is already small enough to be neglected, right? So this should be equal to 0, so I can already get rid of these charges here. And now I'm going to derive this thing again in time, because what am I looking for? I'm looking for an equation that is a kind of oscillatory equation. I want to see n1 oscillating with time. So equations that give you oscillations are normally second order equations in time, right? So I'm going to derive this thing again in time. This is going to be d squared dt squared n1. And I'm going to put everything else here in the other side of the equation. This is going to be minus n0 divergency of dv1 dt, right? But dv1 dt, I can already say that this thing is what I get from here if I multiply this by the mass, of course, right? So I can put a mass here and a mass on the bottom here. And then this thing is going to be the charge multiplied by the electric field, right? And everything is in first order here, so I'm going to put E1 here, and because this is V1 too, right? So now I can already rewrite this thing like this, right? N1, and this is going to be minus N0 over the mass. There should be one charge, one electron charge here, but then I have divergence of E1. Divergence of E1 is going to be 4 pi E. Then this term in first order approximation, in the first order approximation that I'm taking here, this should be divergence of E1, and N is going to be N0 plus N1. So the N0s will cancel out here, and then all I get is N1 itself here. Now there will be another charge that comes from this one, right? And there will be an N1 here. So what I'm saying here now is that the second derivative of N1 is proportional to N1 itself, but with a negative sign, and this is the constant that you put in front of it. So the solution for this thing is either a cosine function or a sine function or a complex exponential and so on. But the frequency of this cosine or sine or anything like that, the frequency would be omega squared, that is 4 pi e squared and 0 over m. And as I have a density of electrons oscillating, what I'm going to say is what I have here is a plasmon. So it's an oscillation of the density of charges. So that's what we call plasmons, and that's why we say that this is the plasmon frequency, right? So this is what I use it to rewrite this thing in the previous page here. See? So 4 pi and 0 e squared over m. So that's why people call this the plasmon frequency. So let us summarize this again. So we are going to write epsilon of omega. This is going to be 1 minus then the plasmon frequency squared over 2 omega 0. Notice that now I'm using omega 0 again. I'm saying that gamma is so small that I can approximate omega prime by omega 0, okay? And I'm also going to make another approximation in this expression that I use it here, which is the fact that you see, there is a kind of a pole in this thing. If I put omega close to omega 0, this term is a lot more important than this one. It's going to give a number that is much larger. If it is exactly omega 0 plus I gamma, then you cancel out everything, and then you have 1 over 0. That's why I'm saying this is a pole in the complex plane. But let's say that you just have omega close to omega 0. Anyway, this thing is going to be much larger than the other one. Actually, this one I wrote it wrong. Sorry about that. That's a plus here, actually. So then this term is going to be much larger than the other one because this one is close to 0. The other one is just like I'm adding numbers here. So it's going to be much smaller if omega is close to omega 0 and gamma is very small. So because of that, I'm going to rewrite that thing in terms of omega minus omega 0 plus I gamma, and I'm going to say that this is more or less all I have, right? So this is approximately like that. So if you want to rewrite these things in terms of real and imaginary parts, you can multiply this this expression by omega minus omega 0 minus I gamma, and omega minus omega 0 minus I gamma, both in the denominator and numerator. So if you multiply that, what you get is something that you can separate, like omega plasmon squared over 2 omega 0. Then there will be two terms. One term is the real part, that is omega minus omega 0, that comes from here, over, and then the denominator is going to be omega minus omega 0 squared plus gamma squared. And you have a term that is minus I gamma, that's the one that comes from here, and the denominator is the same. Okay, so now I can separate these real and imaginary parts of omega. So what I'm going to call ER, epsilon r, is going to be the real part. So this is 1 minus omega plasmon squared over 2 omega 0. Omega minus omega 0 over so this is what we call the real part of the dielectric function, and the imaginary part is going to be just the what is left here. So I'm even going to rewrite this thing like this just for convenience, because it will look a bit more like a Lorentzian function. So what I get here is something like this. So this is a Lorentzian function. This imaginary part here is a Lorentzian function with a width given by this gamma here. So if you plot these things, what you're going to get is, let's make a sketch of these plots. So it's very clear that in the vicinity of omega 0, what you have for the imaginary part is going to be a Lorentzian function with some width gamma, right? And as you look more carefully into this expression here, what you're going to see is something that goes from, if omega is larger than omega 0 or lower than omega 0, then you change a sign in this thing here, right? So you can just check it. You see that this is actually something like that goes like this. So then this blue line is a sketch of what would be the r, the real part of epsilon as a function of gamma, and the green line is what should be the imaginary part of epsilon as a function of gamma, and this is all written in terms of this as a function of gamma here, and this is omega 0, that is the original frequency of my oscillator. So I'm saying that I have an oscillator that started with a frequency omega 0. If I put light with some omega, then I have these dielectric functions that will provide polarizations and so on, right? So, okay, what does that have to do with light absorption or anything like that? That's because let's now take a look at the Maxwell equation for a system with this kind of polarizability. Maxwell equations would be something like, one of them would be curl of the magnetic field. It should be actually curl of H, but let's say that H and magnetic field are the same in the system. So this is going to be 1 over C d dt of the displacement field that we just discussed here, and curl of the electric field should be minus 1 over C d dt of the magnetic field. So now let's take the curl of this second equation. Then I have curl, this is going to be minus 1 over C the curl of B inside this derivative here, that would be c squared, and the second derivative in time of the displacement field, right? And this displacement field, I'm going to already to rewrite it as being epsilon of omega multiplied by the electric field, right? So actually, let us take a Fourier transform of everything and write everything in terms of this omega here. So I'm also saying that the divergence of E is going to be 0. I'm going to choose it like that. In the end, what I get is the Laplacian of every component of this electric field is going to obey this kind of equation here. That is a wave equation, right? So I'm going to rewrite it as the second derivative here will give me something like minus omega squared over c squared. Then this epsilon here will be epsilon real plus I epsilon imaginary, the two parts of this thing, and the electric field here. So let's try a solution for this thing that is in the form of a wave, but with a term that would be an evanescence term. So this would be E of E0 of omega and e to the I. Now I'm going to say that I have a k, that is a wave vector, k of omega, plus an I kappa of omega, and the light is going to be polarized in z direction, so I have only a z direction here. So I have a plane wave for this light, but I have also a kind of evanescence term here, which should be I. When you multiply these two complex i's, then you have minus an exponential of minus kappa z. So this wave function, this function is going to decrease as z increases, right? So then this kappa here will be something like how much of the light field can really penetrate the solid, for example, can propagate inside the solid. So it will give you a kind of a distance where the light can propagate inside the solid. So if you put this equation in these terms, what you are going to find from the Laplacian term, you're going to find something like k plus I kappa squared. This is going to be equal to omega squared c squared epsilon r plus I. So that's what you're going to find. And now you have in the left side and in the right side you have complex functions, right? So in the left side, let's write it again like this. Let's rewrite it like this then. Then 2I k kappa. So now I have a real part and an imaginary part. So this thing needs to be the same as this one, and this one needs to be the same as this one, right? So now we are going to we'll need to solve two equations like that. So let's put these things together here. 2k kappa. This has to be something like omega squared c squared epsilon imaginary. At the same time, k squared minus kappa squared. This has to be something like omega squared c squared epsilon real, the real part of epsilon, right? But there is one thing that we already know here. This is a solid, and or actually this is what I'm assuming it to be. I'm assuming that I have a medium like a solid, for example. Actually, there is a definition of the index of refraction of the medium, and this index of refraction, what I can say is that I have a k that would be the wave vector of this wave that represents light here. That would be a number that I'm going to call n bar, not to be confused with the density that I called n in other parts of this calculation here. So n bar multiplied by omega over c, right? So this is what gives you the index of refraction. So now I'm saying that k is a function of omega. So in the end, this k of omega will also lead to an index of refraction that depends on the frequency of light, right? Which is something that we know actually. We know that the index of refraction depends on the color of the light or the frequency of the light. So one way to calculate that would be to calculate this K that I have here. And the K is connected to the dielectric function of the material, right? So, but what I'm saying with this is that this K is not really free. We know more or less what it is. This K of omega needs to be the index of refraction of the material. So I can write everything in terms of the index of refraction here. So what I'm going to do now is I'm going to get this equation here and rewrite everything in terms of the index of refraction, right? So it's going to be something like K squared, that I'm going to write now as a n bar squared omega squared over c squared. And that should be something like this. And this other term here, I'm going to put it in the other side, like kappa squared, right? So now I'm going to rewrite it also in this way. And then kappa squared, I'm going to use now this equation here for kappa squared. So this is going to give me something like omega to the fourth, c to the fourth, ei to the second, and in the bottom here 4, and then k squared again. K squared again is going to be n bar squared omega squared over c squared. Now I can cancel many of these things here. This is going to be a 2, here it's going to be a 2 as well. And now I multiply everything by n squared. I will cancel also these things here, this and the remaining terms here. So in the end I can find an equation in the form of n bar to the fourth minus e epsilon r n bar to the second and minus e epsilon imaginary squared over 4 is equal to 0. Now the solution for this thing, you can find a solution easily for n squared. That would be epsilon r over 2 plus minus square root of epsilon r squared plus epsilon imaginary squared. We are going to dismiss the solution that has a negative term so that we keep n real. So we are going to get only the positive solution here so that n is always real, because now this index of refraction is going to be square root of 1 over 2 plus square root of epsilon r squared plus epsilon I squared. So in many materials, these the epsilon r is usually much higher in numbers than the epsilon I. So if you want a good approximation for the index of refraction as a function of frequency, that would be more or less like if you say that this term is much larger than this one, you neglect this one, the second one, then you have epsilon r plus epsilon r. This would be 2 times epsilon r. You cancel this 2 in the bottom, and then you get just approximately square root of the real part of the dielectric function. So now I get something that is physical and that is like measurable and so on, that is important, that and now I understand how it comes from. It comes from the dielectric function that I obtain when I have this oscillator model for an electron in the presence of an oscillating electric field. So if I know the real part of this thing, I now can have an estimate of the index of refraction of the system. And finally, for the absorption, I will get the absorption from this equation here. And what I'm going to do is I have 2k kappa. I will rewrite as 2 n bar of omega, right? And omega over c kappa is equal to omega squared c squared ei. Now you can cancel these terms and you obtain something like kappa is equal to omega over n bar omega c multiplied by, and 2, there is a 2 here, right? Multiplied by the imaginary part of the dielectric function. So if you calculate the imaginary part of the dielectric function, what you are calculating in practice is this thing here. And I'm going to define the absorption coefficients as a function of omega. That's going to be the absorption probability should be proportional to that thing. So this is the absorption coefficients. I'm going to call it 2 times kappa, which would be omega over n bar of omega c ei of omega, right? So why am I saying that this thing is the absorption coefficient? That's because by definition, if I have a term that has a kappa that is non-zero, what I'm saying is that this term here is important, which means that the light is not really propagating inside the system. It's dying inside the system. And why is it dying? It's because there is a dipole inside of the system that was induced by that light, and this dipole created, this set of dipoles created an imaginary part for the dielectric function, and this will that will lead to this kappa here that you are seeing, and this will lead to a light that even as it enters as it enters the system, so it vanishes as it enters the system. So it was absorbed by these oscillators that I have in the system here. So what I'm saying here now is that if for whatever reason you have a system where the epsilon, the imaginary part of epsilon, has a peak like the ones that we've just found here, if you have a peak like this, you can fit this peak by a Lorentzian, for example. We just proved that with some approximations. Now, this would be in the vicinity of some omega 0. What I'm saying is that this thing will lead to light being absorbed exactly with that frequency here. So this can be like the oscillator that I'm talking about here, can be many mechanisms that would look like an oscillator. For example, the one that I just mentioned here, the plasmon mechanism, that is also an oscillator, right? So what I have is a set of charges that are oscillating with time. Then if I apply light there, these oscillators will resonate with light in this frequency here, and light will be absorbed. Or if you have, let's say, a solid, then you have a conduction and valence band states, and they form an exciton, for example. Electrons and holes would form an exciton. That exciton, when you look at the imaginary part of the material in the presence of that exciton, you will also find something like this around the frequency of the exciton. And this means that light could be absorbed by an exciton. Or you can find that for a phonon too. That is also an oscillation in the solid, and then this oscillation will lead to a peak like this, and then in that peak around this omega for the phonon, you have like light being absorbed by phonon states, for example. So what I'm showing here is something very general. So you apply this kind of system to this kind of calculation for many systems, but the bottom line here is when you talk about a system where you have a transition that has high oscillator strain, what you are referring to is to a system where this oscillator model would have a peak in some frequency, and this peak is high, and because of that you have light being absorbed in that system with a higher probability, and that's it.